Okay, in this video, we will explain how to compute the Laplace transform of sine of omega t and cosine of omega t. Let me start by saying a few properties that we have shown. We have shown that the Laplace transform of a constant function a is a over s, and the Laplace transform of the derivative of a function is just s times the Laplace transform of the function minus y of 0. And okay, I think this is enough, but let me start by showing a formula that allows us to compute the Laplace transform of the second derivative of a function. And we will deduce that by using this function. Then let's do that. The Laplace transform of the second derivative. But we can say that the second derivative is just the derivative of the first derivative, right? Then the derivative of the first derivative is the second derivative. But then this is the Laplace transform of the derivative of a function. What function? The derivative of the function. Then according to this property, this is just s times, this is the derivative of this function, then this is the derivative of the Laplace transform of the derivative of the function minus the function, the derivative of y with respect to t, evaluated at 0. You see, we are applying this formula, but we are applying it to the derivative of the function. Then, now we apply this formula again. Then this is s times the Laplace transform of the derivative is s times the Laplace transform of y minus y of 0, and then here minus dy dt of 0. Then we have the formula that says that the Laplace transform of the second derivative is just s squared Laplace transform of y minus s times y of 0 minus dy of t times of 0. Okay, we have this formula. But on the other hand, let's consider the function y equal sine of 3t. Let's make omega equal 3. What would be the derivative of this function? Dy dt would be 3 times cosine of 3t. And what is y of 0? Y of 0 is sine of 0 would be 0. And what is the y of t, the derivative evaluated of 0? Cosine of 0 is 1, and then this is 3. And what is the second derivative of y? Is the derivative of this, which is negative, this 3 comes out, and then it's negative 9 sine of 3t. But now, let's apply this formula to see what we get. It says that the Laplace transform of the second derivative of this function, which is negative 9 sine of 3t, right, is equal to s squared times the Laplace transform of the function. But what is the original function? Sine of 3t. Right? And then minus s times y of 0. But y of 0 is 0 minus the derivative of the function at 0, which is 3. What do we get here? Notice that the Laplace transform is linear. That means that this 9 can go out, and then is negative 9 Laplace transform of sine of 3t is equal to s squared Laplace transform of sine of 3t minus 3. And now we can solve for the Laplace transform of sine of 3t. We're going to move this 3 to the left, and we're going to move this 9 to the right, and it will be 9 Laplace transform of sine of 3t plus s squared Laplace transform of sine of 3t. And we can factor our Laplace transform of sine of 3t. It will be factor of 9 plus s squared, and this is equal to 3. That means that we get that the Laplace transform of sine of 3t is equal to, when we divide, is equal to 3 over 9 plus s squared. We have this formula. What happened if we replace 3 by an omega? What formula do we get? We will get that this is equal to, instead of 3, we will get an omega. And this 9 is because you have an omega square plus s square. I would like to point out that this was relatively easy, and it was because of this formula. But if you want to compute the Laplace transform of sine of omega t using the definition, you will have to do an integral, like the integral from 0 to infinity of sine of omega t e to the negative st dt. Notice that we have avoided doing this integral just because of this formula. This is a very powerful formula. Then we have this formula. Let's do cosine of omega t. Let's suppose that y is cosine of omega t. What is y of 0? Y of 0 would be 1, right? What is the derivative? dy dt. dy dt is negative omega sine of omega t, and therefore the derivative evaluated at 0 would be sine of 0 is 0, then this would be just 0. And what is the second derivative? The second derivative would be negative omega squared cosine of omega t. Then notice that now my function y is cosine of omega t. By applying this formula, what do we get? We get that the Laplace transform of the second derivative, but the second derivative is negative omega squared times y. You see, omega cosine of omega t is my y. And then this is equal to s squared Laplace transform of y. Remember that this time y is cosine of omega t, minus s times y of 0. But now y of 0 is 1 minus the derivative of 0, derivative of y of 0, which is 0. How can we solve for Laplace transform of y? Notice that by linearity, this is just negative omega squared Laplace transform of y. I can do the same. I can move this negative s to the left, and I can move this to the right. And then I will get that s, this was moved to the left, is equal to omega squared Laplace transform of y plus s squared Laplace transform of y. Notice that y is cosine of omega t. We can factor omega squared plus s squared Laplace transform of y equal to s, and then we solve for the Laplace transform of y, and we get that this is s over omega squared plus s squared. Then we have shown that the Laplace transform of cosine of omega t is just s over s squared plus omega squared. These are the three formulas that we have shown in this video. This one, and maybe one that is going to be used a lot, which is this one. Anytime we're going to solve a second order differential equation using Laplace transform, we will be using this. In the same way, anytime we're going to solve a first order differential equation using Laplace transform, we use this formula. Okay, this was very important to solve first order differential equations, and this is going to be very important to solve second order differential equations. And we have used this to show the Laplace transform of sine of omega t and the Laplace transform of cosine of omega t. Okay, this is it for this video.